tried it already.
Yeah.
Why aren't you killed?
No, I don't think that way.
Oh, she's sitting next. Well,
Oh.
You excited, Train?
Yeah. Where'd you take this trip last night?
You went on a hike. I got a tick.
Your first tick?
Yes. It was on my hand. Yeah.
You and John.
I know, it was a good spot. Like, but I was just
Defense right after.
No,
Was your defense right after?
just hanging out.
I found any.
Feeling us so connected.
Good, how are you? Yeah, you look great.
I should have brought. You can have it. No, worry. So he has his own family. I don't know if he got opportunity. Like,
Appalachian. That's your dad.
I have a headlamp. You can see.
Really?
So good.
All look amazing.
So good.
Have you been in a room?
No.
You take beers, you put back.
It was a good time, honestly. I put it on for a little bit. I felt like it was bad for.
Yeah, I kind of.
Yeah, it looks really cool. I'm actually gonna be in Rome in 2 weeks.
Or maybe like midday. Yeah.
Oh, do you have any food right now? That's fine.
We just. I don't know.
Looking at the food.
The other ones today.
I'm not kind of sure of your comments. So Alright. I knew you'd ask all that one time. I lost my glasses.
Hi, good.
I literally don't know where I put them.
Yeah.
Isn't that fun?
I'm sorry, Daniel.
I have the prescription.
It's okay.
Yeah.
That comment.
I thought, but I was like, I would
Talk
have.
about how kids.
I think so. How bad is it? I don't know, but I.
Out of my size.
Get it.
No.
I think I just need to go.
Oh, Zach got me my new glasses. That's
I know, if that's your top, it's fine.
While it's stable. Karen, can you hear okay? Someone who's in the phone.
That's actually. Yeah.
You guys things.
You're here early today.
Yes, yeah. If you are doing something, you could chat. Well, I mean, obviously, you're doing something. Yes.
I know, yeah, that's so bad.
So like, hey. Isn't it?
Is that your own sentiment right now?
No.
There's big files, supposed to write some review from the fire and see, and
Right.
I've got everything apart to talk to you.
Okay.
I would like to, come find you,
Yeah, I'll be, it's just
there's a few entries.
all the rest of the week I'll be able to.
Yeah.
I'm only in some
One
morning.
thing that I would like.
Might be a very nice day.
But yes, it might actually be summer, but a couple of days, sort of thing. You know what? Oh, like,
You think so? You like dinosaurs, that's okay. Congratulations. I do miss
Now moved up to where I want.
John. Hi, Alice. Can you hear me? Hello?
Sometime hundreds of years ago, we used to have seminars in the room. Can people who are online hear? Someone please reply back. Tiffany?
Yeah, I could hear you.
Okay, thank you. A lot of shy people.
Hi, Tron. Hi.
Can you hear me, Dr. John?
Are you talking to me? Yeah, I can hear you.
Yeah, we can hear you now. Thank you.
We have the review forms. Hi, everybody. Thank you all for being here today. I'm really pleased to introduce Tran for her master's defense. She joined Dr. Vang at my lab 2 years ago. We were looking for a student to co-advise because we're sharing a lab, and Tran's application just really stood out. It's always fascinating to look back on how a student applied to this place when you get to know them a little bit. But certainly before she came here, she'd done so many things. She got her bachelor's degree in Nong Lan University in Vietnam, and she studied abroad in Hungary while she was there. She did some work in several microbiology labs before shifting over to chemistry. I was particularly struck by her work on Characterization enzymes. She was interested in digesting feathers. Apparently, bird's nest soup is a big deal in Europe, Vietnam. So that sounds great. She, as well as studying abroad in Hungary, she studied abroad in Osaka, in Japan, and in Taiwan before joining here. She's absolutely thrown herself into the life of the lab and the department. She's been a strong contributor as a TA, working in the ice cream short courses, and she's presented several posters within the Penn State community and has won awards for that posters. So I'm really excited to hear how she presents her work today. So thank you, Tran.
The international toxic component is a bit emotional, so sorry. I didn't expect it to be that emotional. Yeah. Like, I'm quite nervous right now. But anyway, thank you very much for your time spent this morning for my visit. My name is Trang, and I'm working with Dr. Zhang at Copeland, and also had Dr. Lambert Science. The past 2 years, working with top equities enzyme Tyrosinase on food waste, extracted, characterized, and applied in food application. So before I talking about too deep about these enzymes and how I do with that, let's talk about the background of this project. Why do I care about this? So imagine when you go into the grocery store, see all of the fast food, massive amount of the apple cider, apple juice, you see ready to eat avocado. You may aware that there is processing food. You may not aware that the byproduct that generate from this processing, there's a lot of byproducts that generate every year. Some of them may be utilized for like compost or compost or like ingredient for animal feed. However, the majority of them being dumped back to the nature for landfill and generate the environmental problem. So scientists trying to utilize this waste into valuable compound to transform from waste to, for example, oil, vinegar, or bioactive compounds. And for the past 2 years, I've been studying on one bioactive compound from these byproducts, which is polyphenol oxidase. So many of you may know what is polyphenol oxidase, but many of you may not know. So let me explain what is this. This enzyme is a class of enzymes including different enzymes called tyrosinase, lactase, and catechol oxidase. This catalyzes one of the two reactions. First is monophenolase with oxidized monophenol into diphenol. The second reaction is oxidized diphenol into quinol. And remember for me that this quinol is the important factor for the food application. So now, what is the difference between these enzymes? The catechol oxidase only can oxidize diphenol into quinol. Tyrosinase and lactase, they act on both monophenol and diphenol, however, their results product is different. The lactase, they generate radical from monophenol, however, tyrosinase, they generate diphenol and then both. So now you may ask, so how do you see the act of PPO in the actual food? Every day you may face to the activity of polyphenol input that you may not aware. Example, apple, avocado, mushroom, banana. When you see the brown reaction, it's made because of the activity of PPO enzyme. But they are so undesirable, and many studies has tried to inhibit this instead of using it in food application. However, scientists found another side of PPO application in food, and because of that, it becomes desirable in those byproducts from these fresh products. So you may ask me, okay, I'm talking about application in food, so what kind of application? Remember I told you about the quinol one. The quinol is really reactive compound that can go further to non-enzymatic reaction to polymerize with other phenolic compound to form a complex structure called pigment, for example, melanin. This is a structure of melanin that you can see color in mushroom. And based on this mechanism, we can design the indicator, food indicator, based on temperature and time. So over time, at different temperature, it will have different color generation, and it can correlate with the food quality. Another way to apply this is this quinol also can react with the thioamine group on the protein chain to cross-link protein together. And based on this, they can design packaging for fruit. This one paper, they cross-link casein, pepsin, and ETCG by tyrosinase and make a bio coat around the strawberry that extend their shelf life to 7 days compared to the control one. Regardless, this application in food, nowadays, there's no available commercial tyrosinase for food application for many reasons. First, maybe we still need a more study on this application and exploit potential in food application. Secondly, it's because tyrosinase nowadays only available for as a chemistry agent. The price from the sigma is really expensive for 1 gram of tyrosinase is 2,500. As far as I know, most of the tyrosinase that commercialized, they are from mushroom. So it's indicated that mushroom is a very important source for tyrosinase. But what is interesting about it? The US, every year we produce almost 300,000 units of a ton of mushroom, but 1/3 of them are waste. Mushroom are an important source of tyrosinase. 1/3 of the mushroom produced in the US are waste. It can be potential source to produce mushroom instead of use commercialized mushroom head. The second thing that is important about tyrosinase from mushroom is that they found that there are 6 different tyrosinase in mushroom and across different tissues, and they have different properties. So the mushroom stem, they expose to different moisture, temperature, and pH compared to the head one, which can lead to possess a different isotope that have different properties. So because of that, I have a question. The first question is that can mushroom stem is a sustainable source for tyrosinase and possess the different property compared to the commercial tyrosinase? So with that, I have to have the first objective, which is extract tyrosinase from mushroom stem and see whether they can cross-link protein as the commercial one. My hypothesis that mushroom stem contain active tyrosinase that have different properties compared to the commercial one, and also the tyrosinase from mushroom stem capable to cross-link protein, which is very important reaction for food application in the future. However, I don't want just to stop here. I want to utilize this byproduct to generate PPO that apply in different type of food. We don't not only have a neutral pH food system, we also have acidic food system that need the use of PPO. But we found that the mushroom itself have neutral pH, the culture really have neutral pH, and the report about tyrosinase from mushroom before have report that they have optimal pH at neutral and not have activity at under acidic activity. So it is limited application in acidic food system. So I then want to explore more type of PPO that can act under acidic food system for this application. Where can I find them? Recall that I told you about the Browning reaction in fruit, right? So fruits like apple, avocado, or banana, they have Browning reaction that indicate the activity of PPO in it. That is the first requirement that the tyrosinase or PPO that extract from this food can be potential for food application in the future. Secondly, it should have acidic pH because the enzyme that naturally acts under that acid condition should have active and stable under acidic condition. So that is the second criteria. And based on that, I specifically choose these three fruits, which is apple, pear, and avocado. They have different pH in the range of acidic pH with potential. And not only because they have Browning reaction, they also is highly demanded in processing food that generate a lot of waste every year, including apple, pear, pomace, and avocado seed. Using this source of potential PPO in acidic condition, I then go ahead to have the second objective, which is extract PPO that potentially work under acidic condition from this selected byproduct and see whether they can oxidize different kind of phenolic under acidic condition for food application. I hypothesize that the PPO from selected acid byproduct have active and stable under acidic pH and also capable to oxidize a range of phenolic compound. So with that two objective, now let's move to my first objective with the method and result. See what I have done with that. Recall that I mentioned about objective and hypothesis. Now I have two aims. The first aim is to extract tyrosinase, crude tyrosinase from mushroom stem and determine its activity. Second aim is to demonstrate its ability to cross-link protein and show it on acid pH. So for the first aim, this is how I extract my crude extract. Our university have the mushroom research center. I collect the mushroom stem from that center. I remove the culture medium mycelium, and then I blend them with buffer for overnight and centrifuge to collect the supernatant I call crude tyrosinase. So now, how do I know that in this solution there's tyrosinase? I then purchase a pure tyrosinase from Sigma to compare with it. So I run them both on ADS spatial. The first line is the commercial tyrosinase. Second line is my crude extract. You can see the commercial one has three thick bands that's the protein pattern of tyrosinase. My extract, even though they have different molecular weight band here, they have three area thicket that also similar pattern with the commercial one, which may reflect the presence of tyrosinase in my crude extract. Secondly, when I compare with the structure of tyrosinase, they have two heavy chains that contain active site in and the two light chains. So after the proteolysis process, it been cut into 4 different pieces. And the heavy chain have molecular weight around 43 kilodalton, which correlate with my heavy chain here, and the light chain have a molecular weight around 14 kilodalton, which correlate with this band. So this compared to the commercial one, and also compared to the structure, it seems that of reflection of the tyrosinase present in my crude extract. However, when I have a closer look compared to my to the commercial one, I found that my enzyme have a slightly lower in molecular weight. it is found in literature that 6 different isozymes of tyrosinase in the butter mushroom would have different in molecular weight. It may reflect the difference in isozyme of the tyrosinase from butter mushroom stem compared to the half one. And they may belong to different isozymes. And because of this, I expect that when I go further for the characterization of enzyme activity, it was different in activity. So how do I know, how do I examine its activity? I base on one reaction, which is oxidized diphenol, which is L-DOPA. And if the enzyme is active, it can transform the L-DOPA, which is colorless, into dopastrom, which is red color. And the increasing of the absorption from the dopastrom over time, I will have initial rate that I can use this to calculate the enzyme activity. Different conditions, for example, pH or temperature, will affect on the reaction. Reaction. So based on that, I can calculate its activity. First, I want to assess into its optimal pH, and let it react, catalyze that reaction from L-DOPA to DOPA under different pH from 3 to 10. I found that at the pH 7.5, it's an optimal pH here, which is neutral that I expected, and there's no activity under acidic pH. When I compare to the commercial one, they have compatible trend, which is not dramatically different compared to each other. Even though they seem to have different in isozyme, they show the same pattern of optimal pH. When I keep this enzyme at those pH for 24 hours, this is what is happened. It's very stable under pH 5 to 10. However, it does not also stable at acidic pH. So it suggests to you this enzyme under the neutral pH system. Next, I want to see how temperature affect on this reaction as well. So again, compared to the commercial ones, they have similar in optimal temperature at 45 degrees C. However, my crude enzyme seems to have a broader range of optimal temperature. So it may reflect of the different isozyme. And so I know that how pH, how temperature affect on my enzyme activity. Now I want to see how it has the affinity toward its own substrate compared to other tyrosinase that's found in previous paper. So this is my enzyme, and this is Km, which shows the affinity toward the substrate. And this is tyrosinase from other source, from mushroom top stem or from recombinant mushroom tyrosinase into bacteria. It is shown that my enzyme have the lowest in Km, which is the highest in affinity toward the substrate, which is L-DOPA, compared to other binding. And it seems that it can reflect on the different isozyme. So the different isozymes can have different affinity toward different substrate, and I have show a very high affinity toward L-DOPA. Also, I found different component, chemical and metal ion can also affect, like inactivated or activated. So that is the first aim that I demonstrate that the crude tyrosinase from mushroom stem do contain tyrosinase, and that is slightly different compared to the commercial one. So now I found that it's comparable to the commercial tyrosinase. Future study, however, needs to investigate how it's different in isozyme by sequencing the protein sequence, or also study on how it's substrate specific different compared to different isozyme. So now I know that my enzyme is compatible to the commercial one. Now I want to ask if it can do the same job with the commercial one. If the crude tyrosinase can do the same job by cross-linking protein as commercial one, do we still need that expensive and many step of purified tyrosinase for that cross-link protein? So to demonstrate that, I then use the crude enzyme, which can catalyze these two reactions to form the protein cross-link. I use 1,000 nanounit of this enzyme to react with the 0.2% of sodium caseinate. And this is how it looks like on the acid phase gel. This is the blend of native casein, and this is the blend of the crude enzyme. You can see the blend of tyrosinase over there. So I take the sample out every 20 minutes to see how it reacts. I expect that the native casein will gradually fading because it's been crosslinked by tyrosinase, and there will be the formation of polymerase of protein on top of the gel. That is the evidence of the protein that's cross-linked by tyrosinase. This is what I see in reality. So I see the native casein does degrading over time. However, there's nothing formed on top. But surprisingly, there's more formation of hydrolyzed casein in the bottom of the gel. So is that my tyrosinase not cross-linked but degrading protein instead? Theoretically, I don't believe so. Then I go back to the literature review, and I found that there are actually a bunch amount of protease in the mushroom extract. They even one paper that you tyrosinase from mushroom to suffer the heat. And that's one paper found that they sequencing the whole mushroom sequence, and then they found 111 genes that coding for protease. And among them, the serine protease is the most upregulated transcript that reflect of the protease activity in my crude extract. So that made me think that, okay, my tyrosinase may actually cross-link protein. However, the protease has interfered the result by degrading all of the casein. So it not allow me to show the cross-link on the acetate shell. Because of that, I decided to employ one partially purified step, which is ammonium sulfate precipitation, to separate different proteins so that I can reduce protease and increase the concentration of tyrosinase. So I use different in ammonium sulfate saturation from 30% to 80%. And this is what it looks like, the affinity, the efficiency of ammonium sulfate precipitation on purified my enzyme. So the fraction of 50 and 60, you can see a very thick tyrosinase band here. And especially the 50% show the least non-tyrosinase band. It's really potential for eliminate non-target enzyme in my extract. And to confirm this result, I tested tyrosinase and protease activity in each fraction. For tyrosinase activity, I can see again confirm the result that 50% shows the highest in concentration of tyrosinase, following by 60 and 70%, so they increase tyrosinase activity. When I test the protein activity, this fraction also decreased significantly compared to the control one for the protein concentration. So this three fraction really potential for the cross-link application again, and also make this is the first combination, and I also make the second combination of 60 to 70% to see different fraction, how can it affect on the cross-link, because they separate different protein at different fractions. So this is how I see the result on the edges plate gel. Now look at these four lengths. They are control ones, so there's no enzyme activity on these band, and overnight there's no effect on the casein band. However, the treatment group with active enzyme, again, this casein band totally degraded. However, the 60 to 70% seems to the tyrosinase seems to outcompete with the protease one that show a smear of different molecular weight band. However, as far as I consider, I want it to be more dramatically cross-linked and more convincible evidence compared to this. So I then choose another approach, which I mentioned to you that among a lot of protease in the butter mushroom, the serine protease is the most upregulating. So I specifically choose inhibitor specific for serine protease. This has been found to effectively inhibit serine protease in butter mushroom. However, they're not food grade, so it only used for me to show the cross-link of the casein, but not for food application. For food application, I try with EDTA. It is a food grade component. However, it's not specifically to the serine protease. it can inhibit metalloid protease, which is not too abundant as serine protease. So I don't expect it to have dramatic effect on protease inhibitor. So this is how it looks like on the gel. It looks like a lot of information. So but now just first look at the first lens. I have only crude enzyme tyrosinase and casein. Again, you can see this is a casein band. It totally degrades into hydrolyzed casein. But once I add the inhibitor, which is the PMSF, at two different concentrations, it shows the dramatically formation of cross-linked protein here. It is a strong evidence of protein that has cross-link based on tyrosinase, and then when I inhibit the protease activity. When I compare to the commercial one, it also shows the cross-link up here, the evidence here. So this one doesn't have inhibitor, doesn't have the protease in it, and it can cross-link protein. So again, the point here is that my enzyme is coenzyme, but it also can do the same job with the commercial one. So it's not necessary to go through all of that expensive purification so that we can bring it closer to industrial application. However, again, this is not a food grade component. Then I again try with the EDTA, which is a food grade. It surprisingly have effective in eliminate protease activity and show the crossing up here, even though they show the more hydrolyzed casein band down here. So in conclusion, for the second hypothesis, I found that the tyrosinase extract from mushroom stem are able to cross-link protein with assistance from the cross-link purification or protease inhibitor, and they show the cross-link compatible to the commercial one. To make it more approachable and also practical for industrial use, I have some thoughts. First, again, you can see that partially purified or inhibitor can help the poo extract to cross-link. So how much purify we need so that can bring it to application without too much step of purification. And secondly, you can see this is my reaction. This is an inactive enzyme, so over time there's no change in the color. The one that with my active enzyme, they change the color to brown. That is the act of tyrosinase on phenolic compound. As I mentioned at the beginning, phenolic compound, they've been oxidized into quinone. This quinone can polymerize to pigment. So that can be the one result of pigment. That can be sensory challenge. However, it also can act as the mediator to cross-link proteins. So for investigators need to know whether this phenolic compound is a sensory challenge for some product, or they can be a good mediator for cross-linking. Besides that, we also want to know how customer will respond about the food that contain this enzyme or the effect of the enzyme on the food texture or color. So that is the end of my first project. Now I want to expand its application with academic conditions. So I was supposed to study about the PPO that can act and stable under the acid condition. So recall about the objective that I have proposed. I have two aims. First is to extract PPO from this acidic product that I select and determine which one is the most potential for act under the acidic condition. And using that one that I choose, I go to the second aim to determine its property and ability to be oxidized phenolic compound under acidic condition. This is the material that I choose. I have two types of apple, two types of pear, and a half avocado. I measure that pH when I extract them, and they have different pH in the range of acidic H. So now I have two methods to extract PPO from this material. For apple and pear, I go through the same procedure. First, I use the juicer to separate the cider, which I consider directly used as a cider PPO. For the pomace, which is the byproduct from the juice extraction, I blend them with buffer, stir overnight, and centrifuge to collect the supernatant and treat it with as the pomace PPO and dissolve the pellet. For avocado one, it's a bit different. I separate the flesh with the seed. Using the fresh seed, I blend them, powder them, and blend with the buffer again, the same procedure to centrifuge and then collect the supernatant. I treat it as avocado seed PPO. After having all of the samples to prepare, I then assess to the optimal pH to see which one of them are active as an optimal under acidic pH. So a lot of result here, but I want you to look at the avocado seed PPO first. So once I blend the fresh seed of the avocado, I see that it dramatically changed the color from off-white to orange. It seemed to have very strong activity of the PPO. However, when I use the assay using ELDOPA to test this activity, it didn't show a lot of activity here, which I cannot see this thing within optimal pH. So there are many reasons for this result. It can be that PPO in the extract in the seed itself is low, or either the ELDOPA is not good substrate for the PPO from avocado seed. Or another way is that maybe my extract method needs to be improved to have higher yield of PPO. But anyway, for this result, it not show the distinguish of optimal pH, so I've not choose to pursue this PPO. I then move to the avocado of the apple one. They do show the activity under acidic pH within pH 4. However, most of them have the optimal basic neutral pH, which is not really potential compared to the pair one. So the pair one have activity at pH 3, and they also optimal at pH 4, 5, and 6. So this is most potential. When I compare again to the mushroom one, I found that the mushroom one again didn't have activity under acidic pH and the optimal neutral pH. So again, I found that these two candidates, anchor and barley pomace PPO, are the most potential as they have activity at acidic pH, and they also have high specific activity. When I keep these enzymes under the same pH for 12 hours, I found that they stable under pH 4 and 5 after 12 hours. When I compare to the mushroom one, again, they're not stable under acidic pH. So that is the first hypothesis that I found. Most of them have the activity under pH 4, and barley and anthropomace PPO have most potential for acid and stable PPO. So I now then use these two candidates for further characterization property about molecular weight and how temperature affect on the activity. For molecular weight, it's surprisingly that these PPO extract, they are crude extract, but they show a very simple band on the HL. There's no commercial PPO from pair for me to compare, but I can compare it with the previous study. It found that the molecular weight band from previous PPO found is similar to the weight compared to which is 44 and 25.6 kilodalton. So it may reflect the presence of PPO and its molecular weight on SFHL. So now see how the temperature effect on them. I let them stay at 4 to 70 degrees C, and I found that they are most optimal at 20 degrees C. The broadest one show a more broader. However, when I keep them at the same temperature for 12 hours, they show the same pattern of stable temperature from 4 to 20 degrees. Okay, now I know they are active and stable under acidic pH. But I keep calling them PPO because I don't know whether they are tyrosinase, peptic oxidase, or lactase. I need to use different substrate to see how a specific of substrate toward these enzymes, so that I can determine what kind of PPO are they. So I have monophenol, diphenol, and different polyphenol compound here. To call them tyrosinase, they need to oxidize monophenol into diphenol. When I let them interact with L-tyrosine, there's no melanin color formation or color changing overnight, which means it's not oxidize the tyrosine to call tyrosinase. They also not oxidize these phenolic compound, meanwhile they can oxidize L-dopa and EGCG, which is diphenol. And so because of this, they can belong to catechol oxidase enzyme instead of tyrosinase. For these two compounds, I will then go further to characterize its affinity toward each field. So they both show the high affinity toward L-DOPA and unshown show the higher affinity toward EGCG. I don't have enough time to run the experiment with the application of this product. However, this L-DOPA and EGCG really potential because at the beginning, when I present about the application of tyrosinase or PPO in food application, they cross-link EGCG with casein and pitasen to make the bio packaging. So this compound, after they've been oxidized, they can form prenome and then can join to different polymerization or protein cross-linking. So it's really potential for food application in the future. For the second hypothesis, I found that they do not act with monophenol, which to call tyrosinase, but they do act with diphenol. At the end, I found that it should, in the future study, I should apply the result that I found about this acidic adaptive PPO and also the substrate that they act on the food system application. And also from the first study, I found that the protease effect on its activity, effect on its ability to show the crossing of protein. And I found that from literature review that protease also present in pear and also other food extracts. So protease needs to be a factor to be considered for future application. Maybe we can recruit partially purification or inhibitor like the first study to stop the interfere of the protease in the application. So that is all of the result that I have been working on. So now you may wonder, so let me let you know that what kind of impact that my studies have on the food system or for the environment. Again, come back to the first story. When you walk into the grocery store, you see all of these products. You now remember, oh, a lot of byproducts generated to the environment. However, after all, my research can contribute to transform these byproducts into a part of other product that is useful for us. And that is all of my presentation of this reference that I use. And lastly, but most importantly, is maybe my research, but also